All right, so what if we don't have a homogeneous system? What if we have a non-homogeneous system, meaning b is not the zero vector? Then what do we do? So when a non-homogeneous linear system has many solutions, then we can find a general solution and then write that in the parametric vector form. So let's look at an example of how we do that. So describe all the solutions of ax equals b, where we have our same A vector from our other example, or A matrix, I should say, and then equals a non-zero. So let's go ahead and get this set up in our augmented matrix. All right, and then when we end up getting down to it, what ends up happening is you get 1, 0, negative 4/3, negative 1, 0, 1, 0, 2, and then all zeros. Because the row operation isn't going to change your A matrix, but it will change what we're equal to here. So that means that x1 minus 4/3 x cubed, x3, I keep saying x cubed, x3 equals negative 1, and x2 equals 2. So I can write my x vector as negative 1 plus 4/3 x3. x2 is always 2, and then x3 here. And I'm going to take a little note from the last example from the previous video, where I'm going to take all the constants and put them in one vector. And then I'm going to take out the x3 and then put these coefficients in a second vector. And if you notice, this is then an equation. X equals, we can call this whatever we want. In the notes it says P, and then this V. And instead of calling it x3, we can just give it a name T or whatever we want to call it. That's just what we look at here. And I want you to realize that if T is 0, then we would just have P as our solution. And then plus V means that this needs to then be the span of all the vectors between P and V. So this is the solution set of all solutions for AX equals B, because x3 is free. If we wanted to look at x, like where is the 0 vector, we knew from before that that was just this guy. Okay, and then P itself, we actually call the particular solution for equal to B. Okay, so this is what like the homogeneous solution piece would be. That's the solution set for AX equals 0. If AX equals B, then we are going to know that this is our particular solution, right? Because if it was 0, then we'd have this is our other solution. We already found that. So P particular solution, and it's because it's equal to B there. So this specific outcome ends up being a vector addition translation in R2 or possibly in R3. So it's the effect, it says here, of adding P to V is to literally just move V around. We talked about vector addition before. And so we're just moving these vectors around through vector addition, where TV, right, was dependent on the homogeneous solution, and then P is dependent on our B solution here. Suppose L is a line through 0, V. So this is line L. Okay, and then we're adding P to each L on the course here, okay, on our graph. So notice that makes a parallel line to that original one there. And the relationship between those two solutions set, okay, here in this figure, is that it generalizes any consistent equation in AX equals B. So remember, to be a consistent equation, we need for the solution to exist, and so this is going to give us the set of all solutions that exist, very similar to the span. Okay, suppose that the equation AX equals B is consistent for some B, so a solution exists. Let P be a solution. Then the solution set of AX equals B is the set of all vectors of this form, where VH is the solution to our homogeneous equation. So again, P here corresponds to our B. VH is going to correspond to our homogeneous, which is what the H stands for. And that's going to end up being some type of parametric, because in order for the homogeneous equation to have a solution, remember there has to be at least one free variable here. And then this says W, we've been using X in this case, and this in R3, this is a really good picture of this in R3 of having like the parallel planes in order to have that P as your solution. So here, your homogeneous solution would be this plane down here, and then you're adding P, so you're just making it move or translate in here. Think about when we did kind of like when we did antiderivatives, and you had like the family of functions like the plus C, because it could be really anything. This is kind of in that way, where like this B here is going to determine where that plus P lands. So here's your solution to your equals 0, and then your plus P vector determines where this is going to be. Okay, without it, we just leave it out. All right, so here's how we are going to write a solution set of a consistent system in parametric form. You're going to row reduce the augmented matrix into reduced row echelon form. So into reduce it down. Okay, express each basic variable in terms of any free variables. So again, in order for us to do this, we might have to have that this is a 0 thing here, so that I have a nice consistent variable. And let's make this a 1 or something like that. Okay, let's put 0 here. So you're going to find that x vector. Writing in terms of any of the free variables, write a typical solution, okay, as a vector whose entries depend on the free variables and those that don't, and then look at this as a linear combination of vectors, very similar to what we did right here. So this is our linear combination of vectors that you would write this in.